Okay, so this is the start of our new unit of our work power machines. This is our first lesson in the unit, which is going to be your favorite probably because it is short and sweet. I mean, very short. Basically, we're going to get down a definition and then a new equation. So make sure that you have your notes with you, your fill in the blank notes, and we're going to jot down a few things. Feel free to pause the video as needed. And what I want us to do first before we jump into the lesson is I want you to answer this question. So in your notes, when I ask you to think of work and what that means to you, or if I were to ask you, what kind of work did you do today? Or did you do any work today? What comes to your mind? So pause the video now and for 60 seconds, write on this topic. Okay, so you may have described work as being some sort of physical labor. You may have thought about it in terms of schoolwork. So if you've been at school all day, you may say, well, I did some math work or we did some language work. But in physics, work has a very specific definition. So we need to make sure that we understand what work means in terms of a physics definition. So let's take a look at this picture and this question. How much work are you doing when you push a wall? Well, the answer to that question depends. Now, this picture, this wall looks pretty massive. So my guess is this guy's not doing any work. I know that because if the guy does not actually move the wall, if he doesn't apply force and move the wall to cover a certain distance, then in physics we say he's actually not doing any work, which might be different than a definition that you came to this lesson understanding. You might say, well, yeah, he's going to sweat. His muscles are going to get tired. Of course he's doing work. But remember, in physics, work has a different definition. So if the wall doesn't move, then no work has been done by this man on the wall. However, if the guy were to push down the wall and it were actually to move a meter or 2 meters, which is very unlikely, but it could happen. So if he were to move the wall, then we could say that he actually did work on the wall. So work by definition is a transfer of energy. And this happens when an applied force moves an object over a certain distance. So we've got some terms in this definition that are familiar to us because we've already talked about force and motion. We know that according to Newton's first law of motion, objects are not going to move unless a force is applied to them. So when you have a transfer of energy that makes an object move because a force is applied, then we say that work has been done on that object. Now, in the next unit, we're going to move into energy. So in this unit, we're going to start to warm up to the definition of energy. We're going to talk about some energy transfer, and then we're going to dig deeper once we get into our fourth unit. So, a couple things you need to remember. Make sure you write this in your notes. Work is done when two things happen. One, a force has to cause an object to move. And then two, the object that moves has to move in the direction of the applied force. So if we're thinking about this guy pushing a lawnmower, if he's pushing the lawnmower and he's applying a force to it, which it looks like he is, and the lawnmower is actually moving and covering a certain distance, which we're going to assume that it is, then we can say he's doing work on the lawnmower. All right, what about here? If we're going to assume that the man in the picture is standing still, it says distance is 0. We can see an upward force on the briefcase. So we know the guy's applying a force to his briefcase. If I were to ask you, is this man doing work on the briefcase? What would you say according to the definition? Okay, does it meet both criteria? Is he applying a force? Yes. Is that object moving a certain distance? And here the answer would be no. So we would have to say that this man is not performing any work on the briefcase because the briefcase is not moving. All right, so here's a different way to look at the definition. So if we know this guy in the picture is lifting upward, And it specifically tells us that the force is perpendicular to the motion. So we're going to assume this man is in motion. So the box is going to cover a certain distance. So remember, we've got two criteria for is work being done. One is the object moving or covering a certain distance. And according to this information that we have, yes, it is. But the second part of the criteria says that the movement has to be in the same direction as the applied force. But here, since the applied force is perpendicular to the motion, we would have to say that in this particular example, no work is being done. All right, so we have a girl pushing a chair here. It tells us the direction of motion is in the same direction as the applied force. That term displacement lets me know that that even though this is a still image, we're going to assume that she is pushing the chair and it is covering a certain distance. So, work or no work? Okay, hopefully you said work because the chair is moving and it is moving in the direction of the applied force. All right, so this is a boy. He's pushing a wall. It shows us the directionality of the force, but then it says no motion, so the wall is not moving. Even if he stands there all day long and sweats and works and he's tired, he is not doing any work because the object has to move. Right, so this is similar to the picture that we had earlier. If you're walking with a book, is it work? And that just depends on a couple of different things. So it depends on how the book is held. If you hold the book out in front of you and the book actually moves in the same direction as the force that you apply to the book, then you could technically say, yes, the book is, you're doing work on the book. But both of the criteria have to be met. So if you're holding the book upward and you're applying an upward force, but you're moving forward, that would not be an example. However, if you are holding the book upward and you walk up a flight of steps, then you would be doing work on the book. So it just depends. Always ask yourself the question. If you're trying to decide if work's being done or not, ask yourself the two questions. Is the object covering a certain distance? And two, is the object moving or covering that certain distance in the same direction as the applied force? So as much as I know you guys despise word problems, we've got some more in this unit, not quite as much as we had in our force and motion unit, but we have two more formulas. So today we're getting the formula for work. We can calculate work by multiplying force and distance. So it's a really simple formula. We're going to pick out the force in the word problem. We're going to pick out the distance, and we're going to just multiply the two. If you like using that pie chart that I talk about in most of my lessons, then feel free to use the pie chart for the work formula as well because it works. All right, so work equals force times distance, and the unit for work is going to be joules, which we'll learn in the next unit is also the unit for energy. We'll talk about why that is once we get to energy. All right, so let's do some practice problems. A crane uses an average force of 5,200 newtons to lift a girder 25 meters. How much work does the crane do on the girder? So if we're looking for work, we're just going to multiply force times distance. Now, if you'll remember from our force and motion unit, force is measured in newtons. So 5,200 is what we're going to plug in for force. And then 25 meters is going to be what we plug in for distance. And remember that vertical line on our pie chart means we're going to multiply those two values. So work equals, when we multiply these out, we get 130,000 joules. So pretty easy. All right, number 2. An apple weighing 1 newton falls a distance of 1 meter. How much work is done on the apple? By the force of gravity. So I want you to pause the video now. I want you to use the pie chart or the formula of your choice. Remember, work equals force times distance. I want you to do this really, really hard problem, and then let's check our answers. All right, so 1 Newton is what we're going to plug in for force, and then 1 meter is what we're going to plug in for distance. And I don't know if you got this one right, but hopefully you did. Work equals 1 joule. I can't promise that they'll all be that easy, but all right, so the brakes on a bicycle apply 125 newtons of frictional force to the wheels, and the bicycle is going to travel 14 meters. So I want to know, how much work have the brakes done on the bicycle? Pause the video now, work out the problem, and see if we get the same answers. All right, so hopefully you plugged in 125 for the force. And then the distance is going to be 14 meters. And so when you multiply that, you should have work at 1,750 joules. All right, so you should have some practice problems that your teacher has given you. You can stop the video now and work on those problems. And I will see you in the next video, which is going to be all about power.